Hi. So my name is David Malin, and this is CS50. So I absolutely love this course. This, for me, is my dream job, to be honest, now teaching this course, because I took this course myself about 11, 12 years ago when I was a sophomore. And I actually came into Harvard not even as a computer science major-minded person, but I started off as Gov. I had exited high school thinking I liked history, I liked constitutional law, and so sort of the natural progression once I got here seemed to be to go into the Gov department. And I spent freshman fall, freshman spring, even sophomore fall, biting off a lot of the requirements for that department, and it was really at the last minute, shopping period during sophomore fall, that I decided, you know what, I'm actually going to give this course a shot. Because I'd always been one of those geeky kind of kids, and I always liked playing with computers. Grew up with a Commodore 64 and an Apple II and a Mac, and then PCs eventually. But computer science and computer science courses, I mean, I actually remember looking around at some of my friends actually in high school who were taking AP computer science, and I thought they were a bunch of geeks, to be honest. And I didn't actually even consider taking that course myself. And freshman year, when I arrived here, I still was sort of the certainly technically minded sorts, but this course, CS50, had this reputation, and it had it for years of being ridiculously daunting, ridiculously time-consuming, and overall scary, and that, quite honestly, that reputation scared me away from taking that course my freshman fall. And this was, mind you, I was working as a UA, and if a UA was a user assistant, if a user assistant was sort of disinclined to take this course, well, I mean, maybe there was something to that. But finally, sophomore fall, I decided, you know what? I'm still going to continue on this Gov track. I'm going to enroll in CS50 pass-fail, because it can take the edge off the course, give me a bit of freedom. And at the last day, literally the last moment, I ended up going to the registrar and filling out whatever paperwork was required to switch myself to a grade. And I ended up switching that winter to computer science as my major. And fast forward several years, I ended up in graduate school in computer science. And then of all things, I ended up here. And it is really a weird sort of role reversal now to be up here, because it was precisely this course taught by a brilliant man at the time, Brian Kernahan, who was visiting and is a pioneer in the world of computer science, that turned me on to computer science and actually got me into this kind of stuff. And then it's not to say that students who take this course all exit as computer science majors. The computer science majors among you are by far the minority in this course. In the single digits, maybe tens %. Most of the students in this course are in fact non-majors. So why might that be? Well, you often hear, whether it's in high school or college, that this is one of those courses that teaches you how to think, problem-solving skills. But you know what? There's actually something to that. Like, I can genuinely say, certainly as more and more years have passed and sort of the more comfortable I've gotten with this kind of stuff, I absolutely sort of approach life, dare say, a little more methodically or algorithmically, at least in terms of what goes on in my head when I'm thinking about some problem, or I'm trying to give someone directions, for instance. I'm much more precise these days. But even more than that, and sort of the fun side effect of courses like those in computer science, is that this computer that all of you have, either on your laps right now or on your desks at home, you, for the most part, use these computers in such a way that you can only do with them what someone else has sort of empowered you to do, whether it's Apple or Microsoft or whoever wrote some program that you're particularly a fan of. And so when you finally, though, take a course, like in computer science, CS50, and actually learned how to program, it actually opens up some really interesting, geeky, but dare say fun opportunities. In fact, at the risk of sort of living a little too long in the past, I thought I'd pull up one thing that I'm very proud of, and perhaps I've beaten a dead horse for some number of years here, but when I was an undergrad, there wasn't internet, so I can't go that far, but there was no way of checking shuttle schedules at the time other than that printed piece of paper. And, this was kind of a nuisance, of course, to have to pull up a piece of paper to find out where you can go on campus. And so at the time, students were really using what was called fas.harvard.edu, which still exists, but most of your friends who aren't in this room right now will never SSH to fas.harvard.edu, so to speak, though you all soon will. But I wrote this program after taking 50 and Computer Science 51, kind of of on a whim. And that program was actually not this one, but it was this stupid program called Menu Boy. So at the time, back in the day, there was like 495 menu, which I don't know if it still exists. Perhaps one of you can try this later and see who you get. But it was this recorded voice from dining services that would tell you, would recite to you every morning what was on the day's menus. And I'm like, all right, well, Menu Man already exists. So I went with Menu Boy, and it was this Unix program that pretty much me, my roommate, and my other roommate could pull up on a computer in our dorm room and check what was on the dining hall menu. Well, mildly useful. That sort of evolved into what was called Weather Boy, which did, as you might expect. That one was kind of a bust, since we just used to look outside the window in Mather Tower, and that was sort of sufficient. So finally, I hit on, you know what, how about shuttle schedules? The irony being, I never actually took the shuttle myself. But long story short, I sat down with the printed shuttle schedule, and I said, all right, I'm going to do this just because I can. And invented a program that I eventually ported to the web, but it still looked like this. And in a nutshell, as you might expect, you can, via a series of menus or shortcuts, say, all right, I'm in Memorial Hall. I want to go to the quad after this. Well, there we go. If you're already sick of this course, you can go in 1 minute's time and catch the shuttle out of here. And this thing updates itself every minute. So that's all fine and good, but not terribly sexy in 2007 and 2008. So the next evolution of this, for me, was not so much the web-based version, but was a version that actually allowed you to text message things. So if you want to play along at home here, if you have a cell phone, if you dial 41411, and then what you have to type is a text message as follows: S-boy for shuttle boy, and then the first few letters of where you are and where you want to go. So mem quad, for instance, is what I'll type in here. If you can actually see this here. S-boy mem quad. It's a little small. But if you go ahead then and hit send, if this program I wrote last year for CS50 has not actually broken in the past few minutes. Let's see. And whatever that is will apparently tick the time away. And, oh, there we go. And apparently, if you can read this, there we go. S-boy says it's 1:21, and you can go mem hall to quad in 29 minutes at 1:50. So we apparently just missed that last shuttle bus. All right, so all fine and good, but come on, we can do better than this. And so just because I could, and just because I had these skills finally, and this perhaps disposition, I thought, you know what? There's so much freely available information out there now. The shuttle buses, as of last year, started having GPS transponders so that the shuttle services folks could track them on campus. And so I thought, you know what? I'm going to see if I can tap into that data feed, integrate it in mashup form with Google Maps, and late one sad night was born Shuttle Boy, the GPS version. And I will be the first to admit, I still think it's the coolest thing that those red dots move as the shuttle buses move on campus. Now, it's not perfect, so you'll quickly learn in this course what a bug is. And so, for instance, if I actually zoom in on this, yeah, the shuttle is not right on Cambridge Common right now. So it's not quite perfect, but I was at least still kind of proud of that myself. So beyond these kinds of fun things that come sort of by nature with the ability to program, I mean, you genuinely learn how to think and how to approach problems differently. Because a lot of what computer science is, it's not actually programming. Even though I've taught entire courses in the past, and we've surveyed students at the end of the semester, you know, what did you get out of this course? What did you learn? And many of them in many courses have been, I learned how to program in C. I learned how to program in Java. And that's fine. And that's true, and that's valuable, and that's interesting, but it's not necessarily everything. Because one of the more interesting aspects of a course like this is that in teaching you how to sort of think differently, it opens you to the possibilities of solving problems more effectively, solving problems more efficiently, saving yourself time by actually writing software or making hardware that does things that would take a human much more time to solve on their own. So case in point, I thought maybe we could humor ourselves as follows. So a natural thing at the start of a semester is you got to take attendance, or you got to take roll. So you start counting in the top right. 1, 2, 3, 4, 5. All right, so we'll be here all day using this method. So what's a marginally better improvement on that? How could I count students in this room more quickly? Take a picture and do it later. Sure. What else you got? What's that? So count them at the door. In retrospect, that too would have been better. What else? Something simple, yeah. What's that? Oh, have everyone text a number and let my computer count. All right, so that's even more sophisticated. I'm going to go with what I learned in like grade school and just count people two at once. So 2, 4, 6, 8. Right? Don't try too hard. I know, first day at Harvard here, but we don't need to go too far here. And incidentally, let's get this part out of the way. So this is a ridiculously large, if not intimidating room, and we have microphones set up down there. I'd much prefer if we can try to turn this course into something that is a bit chatty, that is a bit informal, because I can't even imagine the idea of, as a student, and even now as an adult, walking up to a microphone to sort of admit to hundreds of people, yeah, so I'm kind of confused. I don't really know what you just said. I don't sort of see these kinds of microphones working too well. You're welcome to use them, but let's see if we can do this a little more intimately. So my conclusion was I'm going to count people in twos. So 2, 4, 6, 8. All right, so that's clearly better because it's twice as fast. But if we think a little harder about this problem of counting students, can we do even better than that? I mean, wouldn't it be a really cool thing if instead of just doubling the speed with which we can count students, or equivalently halving the amount of time it takes to do so, what if our algorithm, our approach, our method, not only started off faster, but sort of as I went, it got faster and faster and faster. I mean, it'd be kind of neat if I could start counting in 2s, then very quickly get comfortable with that, start counting in 4s, then maybe 8s, then maybe 16s, and eventually it gets a little confusing. But if you could sort of build up momentum like this, bam, we would be done counting students pretty darn fast. So in fact, I can't quite do that on my own fingers. So what I did was went ahead and put together an algorithm on paper here, because there's this other sort of opportunity in this room to solve this problem. We have not just me as the single brain or CPU in this room capable of sort of independent thought, but we have a couple hundred of you here who can presumably be helping me out with this. And so allow me to ask two things. First, this is also a very impersonal room. You probably don't know all of the people around you. So take a moment right now, if you could, turn to the person on your left, to the right, say hello, house, concentration, all that stuff, and make a friend. All right. All right. Okay. Yes, they're very interesting next to you. Okay, now back here. All right, so you now have a friend, first of all, in Computer Science 50. Now it's going to get a little more awkward again for just a moment, because I need you all to humor me for a moment, and please stand up. Step 1, stand up if you would. So, there are more of you than there are of me. You are all capable of counting, presumably. Therefore, you are capable of executing this computer program. It's pretty straightforward. It's only got 5 or so steps here for if whoever's standing in back doesn't move over to the side. Step 1 is stand up. Step 2, think to yourself, I am the number 1. All right, it's probably not a stretch for some of you. All right. Step 3. Go ahead and pair up with someone standing near you. Add your numbers together. Take that sum as your new number. A little sanity check. If you're following along correctly, everybody's now the number 2. One of you should go ahead and sit down. And repeat per these directions. If you're standing awkwardly, look for someone you can pair up with. Should be just a couple people standing. Couple people left. Almost there. What did you get?
447.
All right, there should be just one awkward person standing before long. All right, these guys are using paper and pencil. That is not very Harvard. It's okay. Just kidding. I'd be doing it too. What do we got? One here, one here. We need a couple of people to pair off. One here. 3. There's 3 of you. All right, combine 2 numbers. 72? Not. Okay. And 113. So what's that? Oh, and 119. So what do we got? What's the total? I'm not going to embarrass myself in doing it up here. What's our total? What's the total? What's that? 399? So the total comes to, thanks to our diligent teaching staff, 399. So close to 400. And that probably took less time than it would. Oh. 400 it is. So what can we take away from that? Well, how many steps did that take? Well, granted, each of these steps is sort of like one big step. It's kind of like one iteration. You went through the process of finding someone, pairing up, taking on the sum, and then sitting down. So if we kind of group that together conceptually as just one step, let's ask ourselves, how many such steps were there? Well, maybe we can answer this by sort of building from the ground up. This is Excel. I'm just going to use it to do some simple graphing for a moment. So if there's 2 of you, it really only would have taken one such step, one such loop or iteration, because the 2 people pair up, one sits down, done. So one step. If instead, though, there were, say, 4 of you, well, that too would still only take not 4 steps, but just 2 steps, because 4 people would pair, the 2 pairs would pair, done. So just a couple of steps there. So if this number then increases, so I'm going to do a little formula just to save myself some time here. If this pattern increases or continues along these lines, whoops, what just happened? If this pattern continues along these lines, where this is a 3 times 2, all right, let's copy that. Paste there. There we go. So if that pattern continues, but in the right-hand column, this just takes us 1 step. This takes us 2 steps. This takes us 3 steps. So this takes us A3 plus 1, and B3 plus 1. That pattern continues as follows. So in the left-hand column, we've got how many students there are, potentially. The right-hand column, the total number of steps. And this is kind of powerful. I mean, look at what it's saying. If we've got roughly 400 students, so somewhere between 256 and 512 students, that only took, felt like longer, but 8 steps, 8 such iterations, maybe 9. Well, let's take a look at what this actually feels like in the long run. If I just quickly grab these numbers, and this is not the kind of stuff we'll be doing in this course using things like Word and Excel, but it's useful just to illustrate this for a moment. I'm going to produce one of these little plots, new sheet, just to show you what this looks like. And what we have on the x-axis here is number of students. On the y-axis, the total number of loops or iterations. Notice what happens. Like, it kind of takes a long time for, relatively speaking, for small groups of students. But look at what happens sort of in the long run. It feels like this algorithm, this approach, this divide and conquer strategy seems to sort of gain speed. The bigger the problem gets, the more effective the algorithm becomes. If we're out at, say, 4 billion students, that's a big room. So 4 billion students, how many steps does it take to actually implement this algorithm? 32. There's only 32 such steps to count 4 billion students, logistical issues aside. Well, let's see if we can't make this a little more concrete. I don't really like to reuse material, but this one seemed to be a popular one last year. This is a pretty big phone book, right? It's a few thousand pages. And this sort of lends itself to this same kind of thinking, this same kind of divide and conquer approach. Suppose that I wanted to look up Drew Faust, so President Faust in this phone book. Granted, it's the yellow pages, it's probably not there, but we'll pretend it's the white pages. How would you, as a fairly intelligent human being, go about finding someone like Drew Faust in the book here? Yes? What's that? Page 1. So we're definitely going with the semi-approach. So page 1, we have the A's. Page 2, still the A's. Page 3, and dot, dot, dot. So right, the worst case scenario there, whoever I'm looking for might actually be at the end of the phone book, certainly not on page 1, and that's going to take a good number of steps. Probably a slightly more clever person is going to do what? All right, you're going to probably start in the middle, if only because it's easy to open the phone book to the middle. You're going to glance at it and be like, oh, M happened to be in the middle of the phone book. Well, what am I going to do next? Well, I already know that this was a pretty big problem a moment ago. But I already know that Drew's going to be to the left. I'm at the M's, which means she's not going to be over here. And this is why everyone liked this last year. So we can literally throw away half of the problem. And now it's half as big. Well, what do we do next? Well, we can sort of resort to that page flipping approach, or we can sort of repeat. We can sort of recurse and do the same thing again. Smack dab into the middle here, I happen to end up at, well, freebie. We happen to end up in the middle here. This is the C's. So yet again, I can literally take a bite out of this problem equal to half of its current size, throw it away, and in just 2 steps, we've halved and then halved, which means quartered the size of this problem. So now extrapolate to some of the data here. If that phone book were actually ridiculously large with 4 billion entries, 4 billion pages, how many times am I going to split and throw half of the phone book away? Only 32 times. What if there are not 4 billion, but 8 billion people in that phone book? 8 billion pages. Well, 33 steps. And that's a really powerful thing. And that just kind of hints at the types of design problems that come up in computer science and sort of the types of work that ultimately come out of, as we'll see, the course's problem sets. Now, it's not all serious and focused on clever approaches. So we have made a conscious decision this semester to introduce as much geek culture to Harvard as possible. Josiah Quincy and James Otis would be so pleased to be next to this right now. So it all began, of course, 10 years ago when Shuttle Boy entered the Harvard lexicon. Now we're going to try to push some lolcats onto the community here. I'll refer you to Wikipedia for more of a backdrop here. But just in the spirit of this same, you know what, I want to do something just because it's neat, just because it's fun, just because I can. And along the way, I'm sure I'll encounter some interesting problems. I, in a moment or in an hour of severe procrastination last night, decided what our website needs in the course is a lolcat of the day. So this didn't exist last year, and this didn't exist on Saturday. But, I decided, who's not going to click on the lolcat? And I will argue, I will put forth that I bet a non-trivial number of you make a habit. Every time you start pulling up the course's website, you're going to click on that link, even though it really does nothing other than show you right so stupid. But how did I do this? Well, I asked a friend of mine, all right, where can I get lolcats? Well, it turns out that sort of one of these sources, the canonical source, is Ican has cheeseburger.com. So that led me to this website here, which if you really have a lot of time to kill, you can search through, let's see if we go to the bottom, the 90 to infinity and beyond pages that have been posted here over time. But what I noticed, what caught my eye at the top of this page is this little thing here. So subscribe to an RSS feed. Now, this is something some of you might already use. Some of you might have at least seen this icon even on CNN.com, New York Times, reputable sites. It's not all geekery. And long story short, what an RSS feed is just a big text file, an XML file, similar in spirit to HTML, which is something we'll use later in the course to make web pages. And inside this big text file is just a lot of links to the current lolcat of the day, links to yesterday's lolcat, and so forth. And I realized, you know what? If there's this feed that the website itself lets people subscribe to, well, maybe I can write a little program that just downloads that feed, simulating a user clicking that link, sort of analyzes all of that text looking for URLs, things like http://, grab that image, and then embed it into our own website, along with a couple of more links, so then it then links back to the original page. And long story short, that's all it took, was sort of an idea, and make it really cheesy, an idea and the means to actually implement it. And so thus was born lolcat of the day. So more of those on an increasingly frequent basis. So who is in this class? So there has been for years a misconception, for instance, that the course is filled only with those more comfortable, so to speak. We adopted these sort of euphemistic labels last year to refer to those students who were, quite matter-of-factly, sort of less comfortable in a course like this with computers, with the internet, with the idea of even being in a computer science course. Then we sort of labeled the opposite, which were those more comfortable. Students like many among you who've taken AP computer science, who, like me, grew up with computers and sort of have been raring to go with an actual computer science degree. And then there's many of you who are somewhere in between. And being computer scientists, we like to collect data, analyze data, and then actually bolster our conjectures with actual numbers. And here you go. So as of last fall, 2007, the percentages of students in the course roughly broke down as follows. 30%, certainly non-negligible, described themselves as less comfortable, the sort who during shopping period were not coming back Wednesday, but fortunately, 30% of them did. I'm among those more comfortable, 20%. So also non-trivial, but certainly not even close to a majority of the students in the class, because the majority really is made up of about half. Majority of the class is made up of people who are somewhere in between. Certainly not the least comfortable, certainly not the savviest, but they're sort of they're somewhere in between the two. And we suspect that those numbers would play out the same. So those of you who are feeling a little less comfortable, I thought I'd try to put you at ease even before we dive into things more sophisticated. This, of course, if you know, is Senator Ted Stevens of Alaska, who had the misfortune of being lampooned by Jon Stewart and the likes a couple of years ago when he was quoted during a very, very boisterous speech about things related to the internet. So what I thought we'd do is sort of establish a baseline as to what it means to really be less comfortable, because I think that will perhaps put a few of you at ease. So let me grab this. It's about a 3-minute clip. Let's go ahead and pull up the following.
Thank you. Right down here. Today's show is a good one. Shawn Wayans. Shawn Wayans will be joining us. We're very excited about that. But I want to talk to you about this exciting thing I've discovered. I want to talk to you tonight about the internet. I'm going out on a limb here. I'm going to stand up and be one of the first guys to say it. I think this is a keeper. I think this thing is here to say, right now, 2 key internet-related issues are making the rounds in Washington, D.C. One involves the Net Neutrality Act, which would allow larger, more powerful corporations higher speed access to customers, establishing a 2-tiered hierarchy amongst, you know what, it's awfully complicated. Why don't I let an expert, say the head of the Senate Commerce Committee, which regulates e-commerce, explain.
The internet is not something that you just dump something on. It's not a big truck. It's a series of tubes.
All right, that might have sounded more like something you'd hear from, let's say, a crazy old man in an airport bar at 3 a.m. Then the chairman of the Senate Commerce Committee, I'm sorry, sir, I don't quite think I understand your dump truck tube symposium. Do you have something a little more practical for me?
And if you don't understand, those tubes can be filled, and if they're filled, when you put your message in, it gets in line, it's going to be delayed by anyone that puts into that tube enormous amounts of material, enormous amounts of material.
Well, there you have it, folks. There's apparently an enormous amount of material clogging Ted Stevens' tubes. Now, perhaps a little fiber optic cable might be the answer. Stevens ended his lecture by offering a concrete example of the problem we face.
10 movies streaming across that internet. And what happens to your own personal internet? I just the other day got internet was sent by my staff at 10 o'clock in the morning on Friday. I got it yesterday. Why?
I'll tell you why. Because the creek run dry is what happened. And there's Comanches in the past and the women in the internet. Actually, why didn't Senator Stevens get it until yesterday? Well, this is just a little bit of a guess here, but maybe it's because you don't seem to know jack about computers or the internet. But hey, that's okay. You're just the guy in charge of regulating it.
So, the segue there is if you are feeling that you don't know jack about computers and the internet, there's clearly people out there who know just a little bit less. And we make this promise now that we will not publicly lambast you as John did to Ted Stevens there. In fact, where are people really coming from who take this course? So almost half of the students who took this course last year had no prior programming experience, 43%. About the same number had a little experience, whether it was a programming class or having tinkered or whatnot. And then there was only 10% of the class who had, quote unquote, a lot, who maybe took not only AP Computer Science, but maybe taught AP Computer Science, or simply was certainly among even those I sort of made fun of back in high school. This, though, there's one other data point we'd like to share as well. So gender. So these were the numbers. Well, it's funny. It's just so these were the numbers last year, and I would actually put forth that these are actually higher than they have been in years past. And long story short, I don't know why there's this discrepancy, because it's certainly not something that has just arisen, but has sort of been with computer science departments for some time. We chatted with former female students in the course, some of the teaching fellows, and there's certainly perhaps some societal trends at play here. I think it's probably fair to say that it's not the case that guys are better at computer science. We've heard arguments like that put forth before. So I don't know, but I can say that we as a course will at least try to do our part to at least take a bigger bite out of the larger slice there to see if we can't try to equalize these numbers somewhat. So whether you're male or female, know incidentally that this Monday, today, this afternoon, this Wednesday and Thursday, we're going to be having some of these very casual should I sessions. So if you ultimately exit this course later this afternoon thinking, I'm still not sure if this is for me, I'm still not sure if I can fit this in, or really whatever your questions or concerns are, the teaching fellows will be holding some casual Q&A sessions at these particular time. And you can, of course, if you're feeling a little uncomfortable, even beyond those, you can send me an internet and we can talk more one-on-one. So let's see if we can't now begin to level the playing field just a little bit. Even if you don't know jack about computers and the internet, you've probably at least heard that the basic building blocks that run them are bits, are the binary system, are zeros and ones. So what does this mean and who cares? Why is this useful? Well, sort of the easiest way to think about these basic building blocks of computers is like little light bulbs or little state machines that can either be on or off. Here, for instance, is an off light bulb. Back in the day when it was easier to sort of turn the room's lights off, we would just turn the lights off and say 0, turn the lights on and say 1. Doesn't really work well in this particular room, so assume that this is our light bulb representing a 0. This is a light bulb that's on representing a 1. 0, 1, off, on. So if you now have this ability to distinguish between two states, so to speak, the something that's on, something that's off, which certainly you can implement clearly with electricity just by using something as simple as a light bulb, or tinier like a transistor or a capacitor, if you're familiar with such terms, you can actually use these as basic building blocks. So how can you actually use just zeros and ones to do everything that that computer is capable of, whether it's sending instant messages, whether it's sending emails, whether it's browsing the web, everything inside of this machine, the cell phones in your pocket these days, boil down to zeros and ones. Well, how can you possibly represent such arbitrary information using such simple bits of information? Well, sort of think back for a moment, if you will, to grade school. So this number here, 123 in the so-called decimal system. Pretty straightforward. All right, so why does that represent the number 123? Well, if I recall, I was sort of taught that this is what's called the ones column, this is the tens column, and this is the 100s column. All right, pretty straightforward. Why is this the number we know is 123? Well, that's because we have 3 ones. So 3 times 1 plus 2 tens, so that's plus 2 times 10, that's 23, plus 1/100, so 1 times 100. And OK, didn't really get very far with that, but that gives me what I know to be the number 1. But there was actually a process there. Each of these digits, so to speak, from 0 through 9, sort of took on different significance based on the column that they were in. Well, binary, the system that computers use, is really the same thing. So up here, I've sort of pre-populated the slide with different placeholders, different column values, because in the world of computers, in the world of binary, where your only digits are not 0 through 9, but just 0 through 1, is you just treat the columns a little differently. So the right one is still the ones column, but the next one over is not the tens column, but the twos column. To the left of that, the 4s, the 8s, the 16s. So the pattern fundamentally is the same. These seem to be powers of 10. 10 to the 0, 10 to the 1, 10 to the 2. Here we have 2 to the 0, 2 to the 1, 2 to the 2, and so forth. But that's all. Everything sort of boils down to the same system. So for instance, if we have 8 bits or 8 light bulbs arranged in a row, just because it's sort of useful to think of bits as being in a clump so that we can count higher than 1, this set of 8 off light bulbs obviously represents the number 0. Not all that hard. This row here instead, with the rightmost one on, that bit is a 1 because the light bulb is on. Well, that thing just represents, all right, we've got a 1 in the 1 column, so that's 1 times 1 is 1. Well, what about the next row? Well, this represents 2 because one of the bits is turned on, is flipped, so to speak, to be a 1 in the 2's column. This is going to be 3. And then what's the pattern here? If there were another row, how do I get to 4? Well, you sort of flip one more up. You sort of carry the 1, so to speak, and then the other 2 guys become off, off. All right, well, what about a little exercise here? So this is what the same thing, just replacing the light bulbs with explicit 0s and 1s. How about this? So you are in what zip code right now, freshmen? 02138. All right? So on a piece of scrap paper in your head, or not at all, how would we go about encoding 02138 in this particular example? All 0s I heard. Excellent. What about the next one? OK, so I'll give you 10 seconds of an at-home exercise. And if you're finding this a little too easy, skip ahead to, the 8. Do the last one. So you're going to be putting on each of these dashed lines in your head or on a piece of paper the value 0 or 1. O2138. All right, not so hard. OK, so that's it, 02138. Now realize we're talking about bits for the most part here. You're more used probably to talking about bytes and kilobytes and megabytes and gigabytes and now terabytes. Well, a byte is just 8 bits, and a kilobyte is just 1,000 bytes, and so forth. And we'll revisit these kinds of numbers, particularly later in the semester when we start talking about data and such. Now I thought I'd give you a little comic strip that was actually printed in a newspaper. If you chuckle at this, you belong in CS50. So now you understand a little bit. Wow, this did not go over funny at all this year. Everyone last year thought this was hilarious. If you're not quite sure what it means, maybe you should ask the person more comfortable to your right or left. So who cares about 0s and 1s? Who cares about the fact that we can represent numbers greater than 1 using multiple 0s and 1s? Well, this is intentionally scary. This is what's called the ASCII table. So way back when, some people decided, you know what, so that computers are useful, and not just calculators, but can actually display alphabetic information, symbolic information, and the like, why don't we use longer sequences of 0s and 1s, like entire bytes, for instance, and map them to, say, letters of the alphabet. So if you look down the middle column, or the third column here, you'll see this is the decimal column. You can pretty much ignore most of the other columns here. But notice that the decimal number 65, some years ago, was sort of semi-arbitrarily decided to henceforth represent capital A. Which is to say, if a computer ever encounters on its hard drive or in RAM a sequence of 8 bits, that when you sort of do all the math with the placeholders and whatnot gives you the number 65. What that means is the computer should display not the value 65 in that context, but the letter A. And thus was born the concept of word processing and the ability to actually communicate in English and other languages. If we fast forward to 97, that was decided to represent lowercase a. And you'll certainly, no computer scientist would memorize, say, this entire chart. But it turns out with just those two, you can kind of bootstrap yourself and figure out many of the other ones. But fortunately, computers generally do that for us. Well, if you have the ability to sort of count in binary, represent larger numbers, in turn represent sort of letters of the alphabet, well, how do you actually store these things? Because certainly our computers don't have millions of light bulbs per se. So what I thought I would do is take a video here, which is a little cheesy with its voiceover, but nonetheless gives an interesting view inside of a hard drive.
The hard drive is where your PC stores most of its permanent data. To do that, the data travels from RAM along with software signals that tell the hard drive how to store that data. The hard drive circuits translate those signals into voltage fluctuations. These in turn control the hard drive's moving parts, some of the few moving parts left in the modern computer. Some of the signals control a motor which spins metal-coated platters. Your data is actually stored on these platters. Other signals move the read-write heads to read or write data on the platters. This machinery is so precise that a human hair couldn't even pass between the heads and spinning platters. Yet it all works at terrific speeds.
And part 2 of that goes a little bit deeper.
Let's look at what we just saw in slow motion. When a brief pulse of electricity is sent to the read-write head, it flips on a tiny electromagnet for a fraction of a second. The magnet creates a field, which changes the polarity of a tiny portion of the metal particles which coat each platter's surface. A patterned series of these tiny charged-up areas on the disk represents a single bit of data in the binary number system used by computers. Now, if the current is sent one way through the read-write head, the area is polarized in one direction. If the current is sent in the opposite direction, the polarization is reversed. How do you get data off the hard disk? Just reverse the process. So it's the particles on the disk that get the current in the read-write head moving. Put together millions of these magnetized segments and you've got a file. Now, the pieces of a single file may be scattered all over a drive's platters, kind of like the mess of papers on your desk. So a special extra file keeps track of where everything is. Don't you wish you had something like that?
It's so educational up until that last part. I did come prepared, incidentally. If you were a little unnerved by all this talk of low-level magnetic particles, I did bring this. I don't think we really need it, though.
This is the on-off switch.
So, what's the takeaway there? Well, inside of hard drives, there are these metal platters. On those metal platters are magnetic particles. And those particles essentially can be arranged, say, north-south, representing a 1, or south-north, representing a 0. And out of those basic physical building blocks, can you begin to represent those logical entities, those conceptual entities like zeros and ones and bits. So enough on that for now. What is CS50? The course catalog description kind of scares with a bit of terms. What does this actually mean? Well, the course's expectations are to attend all lectures and sections, complete 9 problem sets, take 2 quizzes, and produce a final project. There is no final exam in this course. How are grades computed? Most of the grade in this course is weighted toward the problem sets because that is by far where you will spend most of your time. We are all quite familiar with the idea of either bombing a problem set or just being a bad week or something to that effect. So know that you will be able to drop your lowest score on one of these problem sets at the end of the semester when your grade is computed. The quizzes and the final project are weighted as follows, and you may take this course pass-fail. Look to the course's FAQ section in the syllabus for a little discussion on this. Realize that this is, the TFs can confirm or deny this more one-on-one. This course is not so much hard, I think, as it is time-consuming. And that was the case when I took the course, and I do think that's the case these days, but more on that in just a little bit. The course's website is at cs50.net. More on that as time passes, since there's a particularly interesting architecture, as you'll see, underlying that this year. Cloud computing will be the buzzword there. What about books? So there are no required books for this course. You will get plenty of information, we assure you, from lectures, sections, the internet, and so forth. However, if you are the type of student who sort of likes likes the comfort of a book, who sort of needs to have a book in order to take a class, we do recommend a few books. And we recommend them along two different tracks, so to speak. So those of you who are sort of a little uncomfortable or very uncomfortable with the mere idea that you're in this course, shopping it today, if you decide to take it and sort of want to start the course with a bit of hand-holding in textual form, know that this is the book that we recommend. There is no shame in buying a book called The Absolute Beginner's Guide to C. Just realize that this book is not really a reference book. You'll sort of chew it up, learn it, and then that will sort of be it for that particular book. But it's very good for sort of gaining a bit of comfort early on. For those more comfortable, so to speak, this is the sort of book that risks putting you to sleep if you try to read it from cover to cover, but it's a wonderful reference. And it's not really the type of book that you would curl up in bed with and read from cover to cover, but rather turn to the chapter, turn to the index for whatever topic is of particular interest to you there. Do realize that free, if not superior resources do exist on the interwebs, and we link to those on the course's website under resources. For everyone, we recommend this book. This is a wonderfully fun book that goes more into depth on things like those videos we just showed. How does a hard drive work? How does an iPhone work? And things like this, which are rather tangential to sort of the ultimate goals of the course, but are nonetheless interesting and certainly sort of help take the fear factor, or at least the unfamiliarity around some of the toys that we ourselves carry every day. And for that 10% or even fewer of you who are sort of the true hacker-minded types in this course who care about shaving milliseconds off of the running time of your code will know that this is actually a really valuable reference book, and for those types, frankly, a good curl-up-in-bed, cover-to-cover kind of read. I use this myself in grad school to optimize some research code that I wrote, and it's a wonderfully valuable, geeky type book to have. So those are at the Coop. But don't tell them I said this. You'll find them much cheaper online at, say, Amazon.com, which is where the course website links. So, Coop's not here, though we are, of course, on two cameras here. So speaking of cameras, so this course will take place here. It is, however, filmed for students who either can't make a class or who want to review some class. Know that in addition to the course's lectures and these videos, one of the teaching fellows will also take scribe notes during each lecture, and then those will be posted online within a few days, too. Not only as a valuable reference when it comes time for quizzes, or if you want to fast forward to certain parts, or maybe slow down certain parts during which I was confusing, or fast forward through certain parts. Take place on Mondays and Wednesdays, no lectures on Fridays, but what we thought we'd do during suggested in some Q guide-like forms that we have tea with David once a week. I don't really do tea, but I'll do lunch. So what we thought we would do, and we'll see if anyone comes, is at least I would plant myself in one of the dining halls or the faculty club or somewhere on campus on Fridays during what would otherwise be class time to just do sort of casual office hours, grab a bite, and see if we can't get a few people to come spend lunchtime with me, just so we know who to expect so that we can plan accordingly. If you ever do take us up on such an offer, email that address there just so we know who to expect. It's not so much that we think we're going to be overloaded with requests of people wanting to eat lunch with me. So what about this thing? So we are very technically minded people here. And so last year we started podcasting the course. And what that means is these videos are available online in QuickTime format, MP3 format, as well as in Flash format. If you are particularly inclined, you can pull up, God forbid me, on your... Is that good? I still get a kick out of that. But... I don't know who would want to watch a computer science course on an iPod or an iPhone, or at least admit to it. I, frankly, if you can see, actually, lest you think that I'm completely out there. So that's what I have on mine here. Besides that one video of me. But know that that is possible. More interesting than that, though, perhaps, is the fact that, one, CS50 for the first time this year will also be offered through Harvard's Extension School to students who want to enroll, partake in the course remotely via the internet, wherever they are in the world, and receive credit through the Extension School. Because the course is podcasted, we also had sort of random people on the interwebs tuning into the course, and we're going to take things one step further this year. really in an effort to sort of give something back, so to speak, to those out there. In addition to the course being filmed and all of the handouts and all of the problem sets being made available online, we're going to try to take things one step further this year and use technology to further sort of package up a course like this and its content for really anyone who wants to turn in and bootstrap themselves out there, who might not have the fortune, frankly, of sitting down in a room like this. And we will make use of things called virtual machines, whereby, long story short, more on this later in the semester, we will create images of computers that people, anyone out there, can download onto their own Macs, PCs, Linux boxes, double-click an icon, and what they will get inside of their own Macintosh or inside of their own PC is a window inside of which is our own copy of, say, Windows or Linux or whatever operating system we decide to deploy, so that they really have their own sandbox environment with which to engage in the class. And we will also make such images available to students in the course who, even though we provide CS50.net as a course-wide computing structure, if you are particularly geeky and so inclined, you'll be able to really test out these fairly nascent technologies on your own systems as well, and administer your own Linux machine, for instance, within your own Mac or PC. So what about sections? So sections and the course's teaching fellows are an integral part of the course. Sections will supplement the course's lectures and dive into more depth on problem sets and material. For the first time this year, we're going to borrow an idea from First Nights, which is another class that meets in here, and that's about music, and that it too has a range of students' backgrounds, the A sections, the B sections, and the C sections. When I took that course years ago, I was in A or C, whatever sort of the people who don't know much about music were in. We're going to borrow that same idea, and we're not going to use A, B, and C, but describe them as sections for those more, those less comfortable, and those somewhere in between. And we'll take care of sectioning this Wednesday or thereafter. More on that as time comes. The goal for these multiple tracks is, one, we can sort of handle it now, given that the course is sufficiently large, and two, it's to provide not only the more comfortable people with a forum, an environment where they can really ask those questions that might scare the hell out of the less comfortable students sometime, or at least annoy the less comfortable, even students somewhere in between, but can further sort of stimulate themselves by being in a room full of other people who really want to get their hands dirty with some technical minutia, led by a teaching fellow who's just as, if not more, comfortable with that kind of stuff. And on the other hand, we'll have other sections that cater also to sort of the comfort levels of students who just don't have that background or that sort of level of comfort with that sort of material. So more on that later this week. So the course's staff. So this course's staff is perhaps bigger than the average class size at Harvard. So we have over 50 people involved in the day-to-day operation of this course. Some of them are sitting here today who aren't shopping their own classes. Can the course's teaching fellows who are here stand up for a moment? We're mostly grouped here. Oh, wow. So these are just a few of the faces that you will never forget. Nishat Mehta in 1996 was my teaching fellow. Thank you, guys. And I have never forgot the day that sitting in the back right-hand corner of Elliott Dining Hall, he was taking time out of his day to sort of deal with me, who still didn't get these things called pointers. But that was the day where things finally clicked for me. And this is absolutely the sort of course that long after lectures are over and long after, dare say, you've graduated from Harvard, will you remember your teaching fellow in this and perhaps a few other courses as well. Jansu Aidada is the course's head teaching fellow and will be helping with the administration of the course, a lot of the sectioning details, and so forth. She is a face that many of you, I'm sure, will become well familiar with over time. Do know that in addition to myself and the other teaching fellows and course assistants and anyone involved in the course's production, know that you can turn to any of us, and particularly Jansu, for questions you have, for concerns that you have, particularly even this first week. I think she'll be the first to admit that she was certainly at one point among those of you less comfortable. And so if you're feeling a bit of apprehension along those lines, by all means, strike up a conversation with any of us. So what else exists in the way of support? This is perhaps the most beautiful you will ever see the Science Center. So if you look at this photo online, the skies are bluer than they've ever been, the grass is greener, and you will spend time in the basement of this building for this course, where we have dozens of computers that students log into for one-on-one assistance with the course's problem sets in the form of office hours. More on that once we get to problem set 1, really. We also introduced last year virtual office hours, whereby you can log into the course's website, pull up some platform-independent Java-based software called Illuminate, log into what's really a glorified chat room, but one in which you can click an icon to raise your hand, so to speak. A little icon will flash on the teaching fellow's screen, and we can then not only chat with you via this instant messaging window in the bottom left corner, but also see what's on your screen, and even if you let us, take control of your screen and help you troubleshoot whatever bug is hanging you up at that time, whether you're at brain break in your dorm room or even off campus. So we'll be using those as well. So what do we expect in return? So this is the course's workload. This is the kind of course that you learn. It's the sort of material that you learn only by doing. In the course's lectures, I try to present a mental framework for the week, introduce concepts that sort of give you a sense of what the course's content is about. In sections, we elaborate on that, go into additional examples and details, but it's truly in the course's problem sets where you will take the most away from this course. And even though to some of you, particularly freshmen, might think, my God, 5 to 10 hours per week on a class, there are other extremes. So computer science 161 years ago, when I was a senior, I was like 40 hours a week. Now, that's not representative of all of the computer science courses here, but it at least makes this look like a walk in the park. But the upside is, and you can look to the course's syllabus and website and even to current and past teaching fellows and students, we like to think they're a lot of fun. We'll give you a quick survey of them today, but this is absolutely the type of the course where if you do loan us some portion of your life for the semester, we're pretty comfortable promising that you will not only get it back eventually, but also a lot more. So more on that as time proceeds. What then will we be doing in this course? Well, in the first week, including today, we'll bite off some of the basics. And the course will start in a fairly friendly way. Oh, this is an example of this sort of interwebs technology. Hi World is what we'll use this year instead of Hello World. More on that to come. What we'll use in the course's first week, namely Wednesday, is introduce programming itself by way of a really interesting programming environment that was developed a couple years ago by MIT's Media Lab. So we will very quickly next week dive into the C programming language, where we will spend much of the semester. But just to set the stage, I thought I'd pull up this programming environment, which literally allows you to program things by dragging and dropping puzzle pieces that sort of lock together if that makes logical sense. This is not what programming ultimately tends to be about, because clearly this is not the most sophisticated program that one might make. But what it allows us, what it allows you to do in the course's first week, frankly, is one, hopefully have a bit of fun with actual programming, albeit in a playful context, but two, also give you a sense, frankly, of gratification. It's very hard to sort of impress people by typing a command at a blinking cursor and then getting back some hello world kind of response. Much more interesting is, for instance, something like this. Okay, much more interesting for some definition of much more interesting. That's all it does. I will say the music and the flashing lights, frankly, if you watch it late at night, gets kind of trippy. So you might want to pull that one up. Let me pull up one that wasn't made by a student who then distributed the software with Scratch, but rather pull up this, which one of our course's teaching fellows, now CAs, Andrew Barry, one of Harvard's football stars, actually made during our staff training last year. I love all of the teaching fellows equally, of course, but this is kind of my favorite. So let's take a look at what Andrew did.
Weather girl. And have we got news for you? You better listen. Get ready, or
So we'll make that available on the course's website for you if you'd like. Let me ask, at the risk of putting you in what's by nature a little uncomfortable, for one volunteer to join me up here. I need one volunteer. Yes, come on down. What is your name? Greg. Okay, Greg is going to join me up here for just a moment. Greg, you have to be comfortable before you walk in front of 2 video cameras and the entire internet being on the internet. And we'll need you to sign a piece of paper from the lawyers after this. But come on up. So not only with this programming environment can you create these animations, these interactions, you can also take user input and actually create interactive games. So for instance, this was made by Ann Chi, one of our students, now CAs this year, or now virtual teaching fellows. The rules are fairly straightforward. This is scratch revolution, similar, of course, to DDR, if you're familiar. You're simply going to use the left, right, down, and up arrows so that as things are flowing on the screen, you want to hit the key exactly as the colored arrow is lined up on the top. Make sense? All right, all yours. Let's see how you do.
Work it, make it, do it. Makes us harder, better, faster, stronger.
That don't kill me, can only make me stronger. I need you to hurry up now, cause I can't wait much longer. I know I got to be right now, cause I can't get much stronger. Man, I've been waiting all night now. That's how long I've been on ya. You know how long I've been on ya. Since Prince's don't act for ya. Since OJ had isotoners, don't act like I never told ya. You know how long I've been on ya. Since Prince's don't act for ya. Since OJ had isotoners, don't act like I never told ya. Never told ya. Never told ya. Never told ya. Never told ya.
All right, how about a big hand for Greg? Thank you. So we'll make that one available on the course's website as well. And so that's how we'll spend not only this Wednesday in lecture sort of presenting some of the interesting concepts that arise as a result of that, but also to set the stage for Problem Set 0, which this semester will similarly task you with really taking that environment out for a spin and doing something that is of interest to you. In fact, for what we'll call a hacker edition, more on that in a moment, we will also make available these little circuit boards, which have sensors built into them like this little slider, little sockets for alligator clips, a button here. It's got a microphone as well as a couple of light sensor too, so that you can actually integrate not only human input with, say, fingers, but also environmental input as well. So we'll be curious to see what those hackers among you do with that. The week after, we'll be very rapidly dive into C, this programming language called C, where we'll spend much of the semester exploring the fundamentals of computer science and, in turn, programming. In week 2, we'll continue that discussion, but also talk about some real-world applications of the same, focusing particularly on cryptography. Focusing in week 3 then, in week 3, will we then focus on some of those ideas that I hinted at before. Things involving phone books and counting millions or billions of students, searching and sorting, and actually trying to get a sense of just how good or bad your program is based on its running time, given some increasingly large inputs. In week 4, we'll look at data structures, clever ways of sort of implementing programs that need to store more than just numbers and, say, words in memory. We'll also talk about some low-level details like memory management, how a computer actually moves those zeros and ones around, and what risks your computer is at when you, the programmer, don't move those zeros and ones around very safely. Many of the so-called hacks or compromises of websites and servers these days often boil down, still today, to what are called buffer overflow exploits, which relate directly to the world's popular use of C, C++, and similar language that put you at risk, albeit giving you, at the same time, more power over your program of hackers actually getting into your system. Well, in week 5, we'll introduce another element of realism. I spent a summer a few years ago interning for the district attorney's office in Middlesex County, where quite literally the local police would bring in hard drives and memory sticks and sometimes monitors and mice, but we would then look at the data on those machines and try to provide the prosecutors with whatever tidbit of information it was they were looking for. Truth be told, sometimes forensics is not as sexy as it seems to be on TV. Sometimes we literally double-clicked on my documents, and there was the evidence. We, though, will dive a bit deeper. In fact, this is an excerpt from one of the problem sets from the course last year. This was an image we made and embedded a secret murder mystery in. If you think back to childhood, and if you're kind of sort of doing that thing where you focus your eyes trying to stare through the projector screen, it's not that thing at all. So it's actually the sort of thing where you get like that red piece of cellophane plastic in like a cereal box, and then if you hold the piece of red plastic over some otherwise red piece of paper, a message pops through. Well, we gave everyone a graphical image, a digital image like this, and they then had to write a program that simulated that red piece of plastic so as to reveal who it was that had done it. And I think last year it was Colonel Mustard in the study with the candlestick. So that was the solution to that problem. In week 6, we'll return our focus to data structures, talk about things called linked lists and techniques with which you can solve increasingly sophisticated and interesting problems. We'll look in week 7 at things called hash tables and binary search trees, compression algorithms, heaps and tries as they're called. In week 8 then, well, we transition away from our world and focus on C into one that is web-based, where the web is clearly increasingly the place to be when it comes to software development. Google, for instance, has sort of been a pioneer in terms of buying or implementing things like Google Docs and spreadsheets, and even Microsoft has begun to take those same initiatives. So if you don't know it already, we will teach you how to make web pages, XHTML, HTML. We'll teach you a little bit about HTTP and TCP IP, things you've probably heard about, but maybe have not gotten your hands dirty with. We'll introduce at that point PHP and a database query language called SQL. With these languages, will we be able to transition the problem sets from an interesting and powerful but command line environment, so to speak, to one that is browser-based, and spend a couple of problem sets there. In fact, in week 9, will we introduce the notion or the context of mashups, which is this increasingly popular phenomenon whereby people make available different types of programming code online, different data sets, Google being one of them, Yahoo and the like, and you can sort of take all these different data sets and all this different code that other people have written and sort of mash them up together to do yet more interesting things. The sort of canonical one in the world of mashups is taking like Craigslist and taking Google Maps and actually overlaying markers on Google Maps wherever there are apartments that are available for rent. But things are increasingly sophisticated these days. Some of you might be familiar with Google Earth. So Google Earth is this wonderfully fun tool that I was actually introduced to a few years ago when I was just auditing an archaeology course here. We can, for instance, go to 1 Oxford Street in 02138, which is roughly where we are. It's the Science Center's address. If you've never played with this program before, I urge you to spend the next 1 or 2 days playing with it, just because you can literally take virtual vacations in your dorm room. Here we are. Hovering over the Science Center, using the controls here, we can sort of zoom in. We can sort of re-angle ourselves. We can see some interesting 3D topologies there. There's a link to this on the course's website. But what Google recently introduced, for instance, is not only their Google Maps API, with which I did things like Shuttle Boy and the GPS setup, but they also introduced a plugin for web browsers for Google Earth. And one of the things I thought would be fun to show is something that we may end up playing with, this notion of using Google Earth's plugin, which, I wonder if this is going to work here. Oh, had such good momentum there. Let's see if we can do it in IE, if it's going to work. OK, nope. All right, we're going to run this in the background, and we're going to, so close to having every demo actually work correctly. So we might end up playing with one or more of Google's APIs is the takeaway there. If you haven't already played with something like this, I urge you to play not only with Google Earth or this slowly downloading plugin, but we'll also revisit that later in the semester. And near course's end, we actually look a bit at hardware. We will take for granted the fact that there is some machine underneath it all that's actually running our code and in making possible all the things that we do, and talk about what it means to compile your code and what it means to be a CPU. And in the course's second to last week, we sort of take things up a notch and talk about enterprise architectures, talking about, well, what do you need when you want to go run, say, a tech-type startup? What do you actually need to build? What do you need to wire together? What are your alternatives? We'll talk in this week about cloud computing and virtualization, the idea that you don't need to necessarily buy computers anymore and connect them. You don't need to buy hard drives and storage anymore. You can rather pay someone else a few cents on the dollar and just sort of rent computing cycles, rent memory, rent space. And in fact, that is what we'll be doing with CS50.net this semester. Rather than use Harvard's own computing infrastructure, we will literally pay Amazon about 10 cents an hour to use one of their super fancy virtual machines and multiple such instances that we will virtually wire together and create for you all the illusion of one computing cluster that you can then connect to actually work on your problem sets. And the neat thing about this approach is that for problem sets that involve a particularly lot of computation, a lot of use of disk, well, we just have to type a few commands, double the number of computers, quote unquote, that are actually in the cluster. We can then handle that load for that week, and as soon as the problem set's submitted, we turn off those virtual machines, and they're no longer ours, but available for someone else to use. And we'll, of course, in week 12, conclude the course. Well, what about the course's problem sets, where we'll spend most of the outside of class time? Well, problem set 0 will be released later this week on Wednesday. Next week, we look at C in problem set 1. Crypto. In one of the problem sets this year, will you actually try to crack passwords, so to speak, where you will implement software with which to decrypt and or encrypt information, sensitive information, and see what gets revealed. We'll look also at forensics. So in addition to maybe doing that red cellophane tape thing, I will also likely, like last fall, take a stroll throughout campus with my digital camera, snapping photos of some interesting spots on campus onto a normal Canon digital camera with a compact flash card. Unfortunately, I will likely accidentally format that compact flash card like I did last fall. I'll then make an image, a forensic image of that compact flash card, post it essentially on the course's website for you all to download, and then write your own forensic tool with which to go recover all of the JPEGs, all of the photographs that for a noob, so to speak, would otherwise be completely lost. We'll look in problem set 6 at the idea of implementing not just a spell checker, but the fastest possible spell checker, even engaging in a bit of competition optionally with your peers, whereby we'll benchmark your code, post the results on the course's website, and see if we can't get you to obsessively fine-tune your code right up until the time of submission. Last year, toward the end of the semester, the course's final problem set was to implement what we called CS50 Finance, which was an E-Trade-like web-based program with which students, once they implemented it, could get real-time stock quotes from Yahoo, could be given 10,000 virtual dollars in their portfolio that they could then use to buy stocks, sell stocks. So it was an online portfolio management tool. So we'll likely do something like that again, as well as in the last problem set, introduce JavaScript and object-oriented programming, likely the idea of mashups, and do something similar in spirit to what Shuttle Boy, for instance, was. But the climax of this course is absolutely its final project. So the final project will be your opportunity to take your newfound skills and savvy with programming out for a spin and actually make something that's purely of interest to you. Subject to just a few guidelines. We'll encourage you at that point to build something that interests you, something that's actually useful, something that solves an actual problem, be it for this course, for your research, just for fun, but ideally somehow impact campus. In fact, next year, as most of you probably know, the university is changing its calendar, whereby it's a good thing. Exams will come before winter break, which means there will no longer be this month of sort of either slacking or stressing, depending on the type of personality that you are. But it does put a wrinkle in the course's 10, 15-year tradition of having a final project in the course, because we tend to use reading period, if not break, to actually allow you this opportunity to dive in to your own work of art. So what we will do for the first, and maybe last time ever, is culminate the course in what we're calling the CS50 fair. Think back to middle school science fair, but kind of not so cheesy with test tubes and whatnot, but rather an exhibition where we book some really big space on campus, get a couple hundred tables, a couple hundred power cords, maybe a few dozen pizzas, maybe invite our friends at Amazon, Google, Microsoft, Facebook, and the like to maybe bring some t-shirts, maybe some job opportunities, maybe those little squishy balls, and we will invite everyone on campus to see this semester's final project submission. So it's your opportunity to not only show off your work to your fellow classmates, but also to others on campus as well. Not quite sure what will happen with the final project in semester's future, but we will certainly, I think, this semester go out with a bang. So, welcome to CS50. We'll see you Wednesday.
Faster, stronger.
That don't kill me, can only make me stronger. I need you to hurry up now, 'cause I can't wait much longer.